Hello, and welcome to our third lecture for analytical chemistry. Today, I want to start off by talking about a special case when we are considering rounding, and then we will talk about calibration curve. So, this special case, let's point 0. Four, 5, 5. Let's say I want to round to a total of, let's see, 4 significant figures. We would count 1, 2, 3, 4. We would see the 5. We would see that the number to the right of the 5 is also a 5, so we would round up, and this would turn into 1.43. So we would go to a total of 4 significant figures here with the rounding. So let me change this number ever so slightly. Let's say that we have the number 1.425. So oh 3. We would see 1, 2, 3. See next to the 2, I see the 3. We see that the 5 is indeed 5 or greater. And what we would get is 1, 4. So this is what we would technically assume our answer to be based on our normal understanding of rounding. However, here is our special case rule. So we would say 1.42, and then we have the 5. This 5 is saying that we are exactly between 1.3 and 1.4. When we are exactly in between two numbers, when we are rounding, and that first non-significant figure, so this would be the first numbers, let's say this. If numbers to the right of the last sig fig are exactly 5, round to the nearest even. So normally we would, since it's 5 or greater, we would choose this one. But because it is exactly 5, we will actually choose this value right here. So our correct answer would be this one, because 2 is the nearest even number. So let me do a few examples of this. Let's say 3 sig figs. Let's say we have 1.42, say 6, 1.425, 1.4250, 1.461, 1.45. And let's say we're going to round all of these to 3 sig figs. So the last significant figure in each of these are this one, this one, this one. It's the 2 in all of them. Notice how all the numbers are the same to the third place, that intentionally. So we look at this first one and we see that the number is 6. We see that 6 is 5 or greater, but it's not exactly 5. Therefore, we could use our traditional rounding method and round this to 1.43. Let's see what this one becomes. We see we have the 2. It's the last significant digit. We see that the 5 is to the right of it. 5 is 5 or greater. Traditionally, we would round up to 1.43, but because it is exactly halfway between the current number and the next number, we will actually round it to the nearest even digit. So this will become 1.42. We will see that in this case, it's very similar to the last case. We have the 5 here, but we also have the 0 to the right of it. This 0 is a significant digit in the measurement. However, our last significant place is the 2. But the 0 does not have any, how should I put this? Numerical value to it. Therefore, this 1.4250 is in a way very similar to this 1.425. We could say that 50 attached to this 1.42 is still exactly 0.005 units plus or minus from this 2 or this 3. So this 50 is actually not really in terms of rounding. We're still exactly halfway between this current digit and the next digit that would be rounded up to a 3. But because we are exactly halfway, we would still use our new rule, and we will still get 1.42. Now let's look at this case right here. Very similar to, actually no, this one right here. We see that we have the 2. We look to the right of the 2, it's 6. The 6 is 5 or greater, and because it's not 5 or it's not exactly halfway between, we will say that we will use our traditional rules and say this is 1.4. In this case right here, we have a very interesting, change this to decimal place. So we have 1.42501 here. And in this case, we have the 5 and the 0 and the 1. The 501, this 501, is actually slightly higher to this, or closer to the 3 than it is to the 2. So We are closer to 3 than 2. Therefore, this will be rounded 1.4 to 2. Here's our answer for this one. So the idea is if we are closer, if we are more than halfway to our next number, we're going to technically round to the nearest even number. And if we are exactly halfway, we are going to round to the nearest even number. Now I said even twice, so let's give an example where it's slightly different. So let's say 1.435 versus 1.425. So in this one, we could say we are between the 1.4 4 and 1.4. So we're in between these two values right here. This one, we are in between these two values. 1.43, 1.4. So here's our sort of our spread in this in these two examples. But I want to note that here we have an even. This. But here we have an odd. Here we have an even. Here we have an odd. So in all of these examples so far, we have rounded this 1.425 to 1.42. Because if we are exactly halfway between these two numbers, we are going to round to the nearest even value. That has been the 2, because the 3 is odd. In this example right here, we see that our 3 is odd and our 2 is even, so this will actually round to 1.43. In the case that we are exactly we are exactly half between the 3 and the 4. So if we were to extrapolate this a little more, 0.4350, 1.43501. This again, because we are still exactly halfway between the 3 and the 4, we are exactly between those two values. We're going to round to the even value, so this is the value we're going to round to. So 1.4 here. Not right that I did not write what I said I did. There we go. That makes more sense now, doesn't it? And in this case down here, let's see, we are, let's say 3 sig fig still. It's the last digit. So that means we are going to go between a 3 and a 4 again. But because we have this value, 501 is closer to this 4 than it is to this 3, we're just going to use our traditional methods of rounding, and we're going to do 1. So interesting how these values still these we get the same answer in this case right here, even though we have a slightly different number attached here. But this is sort of a special case rule. You might not see it a lot. It's essentially only comes into play if you have a 5 as a value that is to the right of your last significant figure, and then you have to take into account is my if I round up or down, am I going to round to an odd or an even? You're always going to round to an even if you are exactly between two numbers. So that's just the takeaway, I guess you could say, from this sort of special case function of rounding. Another thing just to add right here. I know a few of you asked me this. When we go from relative percent uncertainty, so we are going to go from relative. We'll use E. We'll use E percentage sign left of it. So this will be absolute. This will be percent relative. So when we are going from E percent E, note that E typically, say, should always have one significant figure. So it's typically only going to have one significant figure. So if your E is equal to 0 0.0001 or 0 0.02, 0 0.10003, this would be incorrect. This should be written as this, because we only want one significant figure in our uncertainty. What else could I say about this? That's fine. And let's say that we have an E percent or a percent relative uncertainty. Typically, it's going to be like something like 10% or 0.1% or 20. Now, a lot of the times you may get something like 11%. The rule for this is if you only have one significant figure and that significant figure is 1, you should keep the digit to the right of the 1 and just make note of it. Because it's considered not proper to throw away the digit if your only digit that you have is 1. So we should keep the 1 in this case right here. In cases like, for instance, if you had like 22%, if you were using it strictly for a mathematical equation, you would keep this value. But if you were just using it for a representation, you would probably want to round this to 20%. The idea is you typically only want to have one significant figure if you're going to be representing it, because technically speaking, your absolute certainty only has one significant. So that's sort of the idea with when we're handling these relative uncertainties and absolute uncertainties. Just weird special cases. Um, that's all I wanted to talk about for this special case type stuff, and I will get to actually start talking about calibration curves now. So, calibration curves are the method that we are going to that are pretty much universally employed in determining the analytical concentration of pretty much any species. So this is a quantitative technique. Pretty much the majority of the techniques we do are quantitative in nature. The qualitative techniques we don't really do much of. That being said, there are much. But most of the time, we want to determine how much of something we have and not what. So, how do we do that? Well, the idea is to generate a curve that is typically linear in nature. So we have an xy axis, and we usually have our x as our concentration. And our y is going to be what's known as a response. Typically, what's going to happen is you are going to use some instrument, and there are many instruments you could use to employ this technique. But some instrument will give what's known as a response factor. When you put a sample into the instrument, it's going to analyze it in some way. It's typically could be absorbance, or for instance, if we would use a mass spectrometer, it's going to be the case of our analyte is going to be essentially colliding with a metal plate that is going to send an electrical signal to a computer once it inputs or reads that signal. In the case of what's known as the FID, which is known as the flame ionization detector, which we see on the gas chromatography machine, what happens is our sample is going to come in contact with an actual flame. When the sample hits the flame, it's going to burn up. And when it burns up, what's happening is those bonds between all the molecules or the individual atoms in the compound are going to be broken and destroyed. That's going to release some level of energy, and that energy level is picked up by our instrument. So that's how an FID works. In the case of UV Vis, which we did last week, we will see our sample is going to be, or our sample will hopefully absorb light in a specific region. So we have our machine shine light into our sample, and our sample will absorb a certain quantity of that light, and the remainder of that light will pass through the sample. The machine measures the difference between the initial light that it pumped in and the light that it gets, or the light that is going to be detected back at the detector end. And it sees that a certain amount of light was lost, and that amount of light that was lost is equivalent to the amount of light that was absorbed. And as a result, we know that, in a way, the absorption that the molecule experiences is sort of equivalent to something. And we get this law, what's known as the Beer-Lambert's law, which pretty much states that we shine some light through here. Some of it's going to be absorbed. And some of it's going to be transmitted. And in a way, we are able to determine the difference between the two, and the amount of light that is absorbed is equivalent to the concentration of the species. So if you sort of think about it, the more of something you have inside a solution, the more of a signal it will give off. So the higher the concentration, I'm going to say approximately higher response. And if this is the case, if our concentration is proportional to the amount that it's being absorbed, we are going to get what's known as a linear graph. So at all of these points, we would say that this would be, so we would have, this would be A, B, C. So all of these values on this line are equivalent to some specific concentration that we know because we measured and prepared it beforehand. So these A, B, C, and D would be known as standards, also known as calibration standards. So what this is really doing for us is it's doing this really awesome thing. It's allowing us to now determine the concentration of some unknown species. So let's say now I have no idea, some concentration of some species that we want to measure, and we prepare it in solution, and we put it into our machine, and our machine says that we have a value of right here for our analyte, of our unknown. We know that we have this nice curve right here. This means that our analyte must, absolutely must, be equivalent to whatever this concentration is right here. So this is the main premise, or the idea that we'll be using to pretty much determine the concentration of any sort of analyte in any sort of solution or whatnot. We essentially generate a curve. We use this curve to then analyze an unknown and compare our unknown response to the response of our calibration. standards, and as a result, we can determine the concentration of our unknown. Now, this also holds true if, say, we do not have a linear graph. We could have a some sort of quadratic or cubic, or we could have some weird shape or whatnot. This is typically not the case. We're typically going to be analyzing something that is going to be linear, but just because it's not linear does not mean it's not capable of being solved. We will just need to employ a higher level of math when analyzing this. This is where computers come into handy. There's a lot of very, very, very nice graphing software that if we were to, say, plug in some points on here, it will spit out some y equals something, something, something. So we would have the equation to this blue line right here. And if we have the equation to this blue line right here, and we know the response from an unknown value, all we need to do is substitute our red values y into this equation and solve for x. So that is the primary idea here. We are going to be creating these lines. Then we are going to be creating equations from these lines. And then we are going to be solving for an x value based upon a y value. Let me discuss the 3 different methods of doing. First, we have what is known as external standards. External standards are the typical way that, or actually the most straightforward and simplistic way of analyzing an unknown's concentration. This is the method that we will mostly employ in pretty much all the labs we do because, well, it's the easiest. And on top of that, the other 2 methods usually aren't required unless we have a particularly tricky solution or particularly tricky analyte that we need to quantitate. So, what is going to happen in our external standards? The idea is that we have our unknown. We take our unknown, and we take some known quantity of it and add it to a solution. And usually our the solution we're going to use is water. So we're going to have a solvent of water typically. And so this right here, this whole thing is known as our sample. Sample contains our analyte that we want to quantitate, and that is typically all we are going to do with our sample. We're going to prepare it in a way that we typically dilute it because usually our instruments are too sensitive to measure a very concentrated dosage. So we will typically dilute our sample down to a much, much lower concentration than where it is found. All that's important is that we know the mass and know the volume. Because if we know those 2 things, we could simply work our way back to the initial amount that we added in so we could find what the concentration of this is. So, After this, we prepare what are known as our calibration standards. So what are our calibration standards? Our calibration standards contain our analyte in a known quantity. So how do we do this? Typically, we will create a stock. Our stock is going to be our calibration standard at its highest concentration. So we're going to create a stock. So analyte at highest concentration. After that, we are going to take our stock and we are going to dilute it into several lower concentrations of what we started with. So we will typically want 5, 10 calibration standards. So if you have a 100 millimolar stock, you would produce a 20, not 20, 80, 80, 60, 40, and 20 millimolar. So that you have a total spread of 100, 80, 60, 40. And sometimes you could take a blank. Usually, it's not always done though, because typically the instrument will actually do a subtraction from all of these. As a result, the blank is already subtracted. Typically, if you do have a blank, it's always going to be 0 here, and forcing our curve through 0 is not necessarily something that we want to do. So typically, we won't have a 0 concentration because it could skew our values. So now that we have our calibrations, our calibration standards, we could run our samples through the instrument. And we will create a graph. So we would have, say for here, 20, 40, 60, 80, 100. And what we would do is create a regression line, and I'll show you guys how to do that in Excel. This is what you're going to be doing a lot. And the regression line will use a formula to calculate a line of best fit. which will essentially cut through all of these points in the best way possible. So the weight of all the points are evenly distributed this line. And we would have our regression line right here. And a regression line would be some y equals mx plus b. We would also get what's known as an r squared value. Typically, we want a 0.9 or greater. So we want value as close to 1 as possible. 1 would mean that our points are perfectly linear. The lower our value becomes, the less or more scattered our points become. So we want a very low r squared value to get a very low scatter of points. That is the big idea here. Typically speaking, our instrument should all be able to give us very, very nice calibration curves for everything that we do. Finally, the next step, we are going to take our analyte. So, or not our stock analyte, the one that we prepared right here, and we are going to run it in the machine. Run stock. Our stock is going to essentially come up right there maybe, and what we are going to do is we are going to use this y value right here, determine this x value right here. We essentially could just use a little bit of math to essentially do take our equation, do y minus b divided by m plus x. So this is the formula we will use to determine our essentially all our values. So y is typically the response. And x is typically the concentration. Response. So this is typically the method that we will use almost all the time for quantitating everything. This is the typical method that we'll use. For pretty much all of our labs, this will be what we will be using to determine the concentration of our unknowns if we have one. But yes, this is the general idea here. Now I want to go over the next two that we'll not see as much, but they are very useful. We'll probably actually employ them at least once this semester in the lab. So the idea here in this next one, we have what's known as an internal standard. So in our internal standard, what's going on is, well, we are going to take our a single calibration standard. Right. We are going to have two standards. Not a single. The internal one, we'll say that's internal. and calibration. And the calibration is very similar to what we talked about last time. The difference is this internal standard. So this internal standard is added to analyte, say sample, and calibration standards. So what is the purpose of this this internal standard? So let's say we have this sample right here. We are going to put our unknown into it. We are going to put our internal standard into it. And we are going to put water into it. This would be our sample. So now let's say our calibration standards, what we're going to do is we are going to there's two ways this could be done actually. Five times. Why am I trying to draw this? So here are our 5 calibration standards. So let's say we have 1, 2, 3, 4, 5. Into each of these, we are going to put internal standard we're going to put water, and we are going to put varying let's say analyte. And we will place the analyte in here as such. Say that. Standard 1, 2, 5. Say this was internal standard concentration. Let's say this is 50, 50, 50, 50, 50. Let's say that we have analyte concentration. We have 20, 40, 60, 80, 100. So what happened was we put the same quantity of our internal standard into each of our calibration standards while we varied the quantity of our analyte. What is this going to do when we run our graph? Well, we are going to essentially, if we graph this, let's say that my analyte will be this line right here. And my internal standards, this line right here. This will be the IS. This will be the analyte. Now, this is an ideal situation. This is response. The idea of adding this internal standard to our sample is that when we prepare anything with our sample, or if we do anything to our sample, it's going to affect our internal standard. Is that not so? Because if we lost some sample, we would lose some internal standard. If we changed our sample in any way or any loss occurred, our internal standard would be affected in a very similar way. The idea is you want to use an internal standard if you have any sort of prep work that needs to be done to your sample beforehand. For instance, let's say we needed to extract our sample from some bark or something. For instance, we wanted to look at the concentration of some chemical that naturally occurred in some plant. And it was a sort of a long process to extract it. Before we would begin our extraction process, when we put our bark into our initial vessel, we would add an initial quantity of our internal standard to that vessel. Then, after we completed our entire workup on the sample, we would then have this guy right here, which is our initial sample ready to be analyzed. And this sample right here would contain the internal standard as well as our unknown analyte. And if anything happened to our analyte in our process of preparing it, we would expect to see a similar thing occur to our internal standard. The idea is the internal standard will react in a similar way to how our analyte will react, but we know how much internal standard we start with. So the idea is if we measure the internal standards fluctuation with how our analyte fluctuates, we could determine or come to a more accurate representation of what our analyte's concentration actually is. So this is not what we actually do. What we actually do is we will take a graph and it will be of concentration. And over here for our y-axis, it will be response, analyte, response, divided by internal standard response. So what's going to happen is you're going to get this ratio. And this ratio is going to respond to any sort of fluctuations that occur during sample prep. I should also note that this idea of using an internal standard is very powerful because it also accounts for any fluctuation in your instrument. Because although your instrument can vary from run to run, say you ran your instrument once for a very long period of time, you may see fluctuations in the response it gives from the beginning of your run and at the end of your runs. If you run an internal standard, because the idea of what you're doing is taking a ratio of how the internal standard responds to how the analyte responds, because of this, you could account for those fluctuations in the instrument and actually eliminate them. So by using an internal standard, you generate a very powerful, you're using a very powerful tool that will account for any variation or fluctuation that may occur in your analysis. So you're still going to generate this linear line right here. The only difference in this line is you are going to be getting a value of concentration versus analyte over internal standard response, as opposed to concentration versus just analyte response. This is the difference in how we are going to determine our concentrations. And when we run our sample through, we're still going to get our sample to occur at some point right here. And we are still going to have our calibration solutions occur at points along here. Everything remains the same. We just do an initial piece of math first to our numbers, and we plug these in. And let me do a little bit extra thing here. Since this approach will typically be done on a chromatography machine, let's say that we get 2 peaks. And let's say this is our analyte. This is our internal standard. These peaks will have values associated with them. Some absorbent counts. It's typically in milliabsorbent units. MAUs. And let's say this is like let's say this is 10. Let's say this is 2. We would simply do 10 divided over 2. And this would be our response. That we plot on the y-axis over here. So we're going to get a bunch of these chromatograms, or what these are called, and we are going to take the values that we get from them, and we are going to divide them from one another. We're going to take our analyte's value, and we're going to divide it by our internal standards value, and we're going to get a ratio. And we're going to do this for each one of our samples, and we're going to do this for each one of our calibration standards. So our calibration standards and our samples will look very similar. Only difference is usually these numbers here will change. This is the idea behind the internal standard approach. Lastly, I want to talk about standard addition. Standard addition is the most difficult of all of these to do, and it provides a very rigorous proof of you do have the concentration that you are stating that you have. So, when what standard addition is good for is for combating what are known as matrix effects. When we talked about solutions, we had our solute and we had our solvent. Typically, our solute is our analyte. But we could have multiple solutes in one solution. But we only care about this one solute, this one analyte. What we are going to say is we have an analyte and we have a matrix. Analyte is what you want. And the matrix is everything else. Now, in a lot of the cases, our matrix will not cause us any issues in the case of our experiments that we did so far in the lab. Our matrix did not interfere in any way. But if you do recall, the soda that we used for our experiment was clear and it was not colored. And that is because a portion of the matrix in the colored soda prevents us from analyzing the soda using just UV-Vis methods, because what's going to happen is that that colorant, that color is going to cause the light that's absorbed to not be accurate. We're not going to get an accurate result from our experiment. And as a result, we can't use the typical method of just UV-Vis spectroscopy for analyzing the concentration of a soda that has a colorant in it, or any sort of dark color to it, because it's going to affect how light is absorbed, obviously. However, if we use a method known as HPLC, which we'll be using this week, we will be able to separate that colorant from the rest of the solution. So we could actually separate the analyte from the matrix, and as a result, we won't have to necessarily worry about matrix effects. However, this is not always the case. It may not always be possible to 100% separate the matrix from the analyte. Or, for instance, we may not be able to prove that we 100% separated the matrix from the analyte. And so we need some way to confirm that if the matrix is still there, it's not interfering with our analysis of what we are looking at. So this is where the idea of standard addition comes in. And this method is a little bit strange compared to the last two, but it provides a very interesting result. So let's say, so we're still going to create our calibration samples. So we have, let's see. So now let's call this sample 1, 2, 3, 4, 5. So we have six containers here. And what we are going to do is we are going to add to each of these what is known as a spike. How are we going to add this spike? Well, let's say this is concentration 1, this value right here. is going to have 0 spike. This one, let's say we're gonna have 2, let's say 4, 6, 8, 10. So to each of these, we are going to add this spike. And what is this spike? So the spike is going to be essentially, it's going to be some concentration that we created. How are we going to do this? So we are going to create a stack solution of analyte. Let's say 100 millimolar. And that's what the spike is going to be. And let's say this is 0 milliliters, 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 milliliters. So at this point, to each of these containers, we put 2, 4, 6, 8, and 10 milliliters of this spike volume to our solution. Now we're going to add something else to our solution. We are going to add, our actual unknown. But first we're going to do one thing to it. So let's say we take our unknown. Like we usually do. File. We're going to add it, this right here. And we're going to add some water. So this will be our sample. So here we have a solution containing our sample that we want to analyze. And so what we are going to do is we are going to add this solution. Actually, up here. Say this stack. So we're essentially going to take this stack, which has 100 millimolars of our analyte in it. And we are going to add 0, 2, 4, 6, 8, and 10 to these 6 different vials. We are then going to add our sample. And let's say we add 20, 20, 20, 20. And now let's say we add water. So let's say So how much do I want? Say 80 milliliters here. Let's say 70 milliliters here. Let's say 8, 76, 74, 70. So ideally, since these would be all volumetric flasks, you wouldn't have to measure out this H2O. You would just fill the flask up to the up to its fill line, and you'd be done. But the idea here is you just want everything at the same volume. So what's going to happen is you're going to have your sample and your analyte spike mixing together in some degree. And what's going to happen? Well, what's going to happen is if you do have any matrix effects, it's going to appear in every one of these samples except for our zero value of zero spike. So how are we going to plot this? We are going to plot this spike versus response. And we're going to get some curve that looks like this. Let's say, so we had spikes of 0, 2, 4, 6, 8, and 10. So we have 0, 2, 4, 6, 8, 10. Here is the plot we're going to do. What we want to ascertain is this value right here. Because what that value is going to give us is the concentration, well, of our unknown analyte. So how are we going to do this? We know that our equation is y equals mx plus v. So we want to set our, well, we want to see when our y value equals 0. So 0 equals do is we're going to subtract b. So we're going to get negative b divided by m equivalent to x. So this is going to be the value. Our x-intercept is going to be our concentration for our unknown value. This is how we determine the concentration using a spike. So the idea here is we're going to create 6 solutions. Each of these solutions are going to contain a varying amount of our spike. So in the same way that we created solutions up here for the internal standard and the external standard, we're going to create solutions in the exact same way for the spike. So in this one, we used 2, 4, 6, 8, and 10. The only difference is we're going to have one of these spikes be 0. The next thing we're going to do is we're going to put the same amount of sample into each one of these containers. So what's it going to do is we're going to see how much this value affects this, 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 so on and so forth. And what's that going to do? That's going to essentially give us a line. That line is going to intersect with our x-axis at a specific point. And that x-axis's intersection point is what represents the concentration of our unknown analyte. So this is a method that we would use if we typically are going to be dealing with something that has a very tricky matrix. And by a matrix, as I stated, it has something inside of it that we are unable to get rid of. And we need to determine if that thing is causing any issues with measuring our sample's concentration. So the last thing that I want to do is actually open up an Excel document and show you how to do all this nice stuff. It's that. I'm going to pop open Excel. And we are going to start with our external standard example right here. So let's call this sheet external sample. So how are we going to do this? Let's say that we have let's say we need to have a stock concentration. So let's say that for now. So we have samples. Let's call them sample 1, call them 2, 3, 5. And let's say that we have a concentration on those samples. Not even value. Finally, we're going to get a response. So let's say the concentration of the first sample is, let's use typically what we've been using, 20, 40, 60, 80, 100. And let's say the response is, let's say 2.36, 3.5, 3.8, 4.7, yeah, 6.28. So we just created some values for a response. Your response could be anything. It's whatever the instrument will give you. When we did our experiment, we used the height of the peak. So here we would use the peak height, and here would be use the concentration that you actually calculate. At this point, what we could do is generate what's known as a scatter plot. So we would go to insert on the top here. We could go to this, no, wrong one. This one right here, insert scatter, insert scatter. Shrink it a little bit. So here is our scatter plot. We're going to select data. We are going to go to add, and then we are going to select series X values. You could hit this arrow right here. And so we're going to select our X values. Remember, we want to use concentration as X. So we'll use concentration as X. We will then hit enter on our keyboard. We could then select Y values. And the Y values will be the response. So we could select going down like that. And we hit enter. And then we could hit OK. And then we hit OK again. And what we just did is we generated our scatter plot. If you want, we could add a title. I'm going to delete this. here is how our plot looks. Now we're not done yet. We want to move over to our graph. We could select on one of the dots and right click the dot, hit add trend line. When you hit add trend line, we get this panel that opens on the right. This is going to be a linear trend line. If you recall what I said a little while ago, we will typically be dealing with linear trend lines, but this will show you how we could deal with those other trend lines that would not be linear. We can look at exponential, logarithmic, polynomial, power, and moving average. And this Excel is not the only only program we could use. Other really nice programs to analyze this stuff that are really nice. But in our case, we will use linear. Linear is good. We want to display the equation of the chart, and we want to display our R-squared value. So let's move down. We no longer need the sidebar. So at this point, you would be done. We would be complete with our entire problem right here. So we have our line, we have our equation, we have our R-squared value. All we need to do is to determine the value of our unknown if we were given one, and we would plug it in and solve. But let me show you how to do something a little bit more neat that Excel could super help you out with. Let's move all these values to the side. This. Pull this over here. Wait to the side. Let's say that our stack concentration, because we never prepare things perfectly, our stack concentration was 105. Now let's say this is in millimolars. Let's say to each of these, we added some volume of this stack. So to this, we added 20 milliliters, 40, 60, 80, 100. Let's say the total volume is 500 milliliters. Typing this uselessly like that. $500 mil. We need to figure out the concentration now. And instead of actually doing math and calculating all of this out like we normally would, let's use Excel to help us. So we would start by hitting equals. And so what we're going to use is the M1V1 equals M2V2. We have we have our initial concentration, which is right here. So we have our M1. Our V1 is going to be the concentration that we add. So it's going to be this so far times this. So initial concentration, initial volume equals final concentration, which is what we want, multiplied by final volume. So we're going to divide the final volume by that whole thing, and therefore we're going to divide this by the final volume. The final volume is the sample's total volume, which is this. And we are given a concentration. And what we could do, we need to fix this up a little bit, because when we shift this entire formula down for the rest of these cells, we don't want the concentration of the stack and the sample of the volumes to shift with it. We want to keep those the same. So we're going to put a $sign before the B and before the 2. And we are going to put a $sign before the B and before the 3. And we hit enter. Our value stayed the same as we would expect, but now we could pull this whole thing down. So now we actually have our new concentrations. And this is actually what I would probably recommend you guys doing when you do your lab reports. I would recommend determine the initial concentration that we established, or that you established when you added your amount of mass to your initial 1 liter solution. And then you could calculate the concentration of the stack. And because you used volumetric pipettes, we could say that we indeed added these specific volumes. We could use those values in this column right here, and then use the same math that I just did to come up with your new concentrations. So our responses remain the same. So what we're going to do is we're going to right click our graph. We're going to select our data again. We're going to edit our series. We need to select our X values. Just selected them, hit enter, and our graph is back up. We have our new graph, we have our new equation, and we have our new R values. Now, let's take this one step further. Let's say we have our unknown response. So the unknown response, let's say, is 3.39. Let's say 89. 3.89. Let's say 3.89 is our unknown response. Let's say unknown, instead of unknown response, we're going to use unknown concentration. Excel is super useful because you could actually give Excel the information that it needs to calculate the concentration of our unknown. And how are we going to do this? Well, start with an equal sign. And what do we need to figure out? We need to figure out if we take our y value here. This is our y value, this is our response, and we plug it into this equation right here. What is our x value going to be? So what we want is to do is take y minus b divided by our slope. So how are we going to do this? There's actually several commands that we could use to essentially do this. So y minus b divided by slope. This is the equation. So this equals, well, it's going to equal y. Well, this is our y value here. Minus, well, what is our b? Our b is known as our y-intercept. So we can start by typing equals I, N, T, and here it is. Here is our first function that we want. We want the intercept function. So we double click it. And now look what it wants. The intercept function takes 2 variables, known y's and known x's. So what we're going to do is take our known y values, which are this, then add a comma. Now it wants the known x's. Our known x's are the concentration. And now we can actually close that in brackets now. So far, we now have y minus b. This function is now going to give us our b-intercept. We need to do one more thing, and that is we are going to divide it. Well, we're going to divide it by the slope of this graph. So what is the slope? Well, I'm going to use the exact same idea. Equals slope. We're going to see slope. What does it want? Known y's, comma, known x's, close parentheses. Now, at this point, we are nearly done, but I want to make note that order of operations is incredibly important. Y minus b over slope means y minus b has to be carried out before the division. So we need to put brackets. Brackets before the b5, brackets after the intercept. And let's see, I found a typo here somewhere. So where is this correction going to be? B5 minus intercept. G3, G7, comma, F3, dot, dot, F7. This one, the slope. I don't know what it's correcting. Looks exactly the same to me. But, yep, here we go. Here is our value, and here is our things. We have B5, which is our our y value, minus our y-intercept, divided by our slope. So this is actually a completed Excel sheet. You could use all these formulas to essentially pretty much do any of the problems that we would talk about. Let's go over an internal standard now. So let's say that we have, let's actually copy nearly everything. Creation of stack, volume of samples. Let's use 500. Let's use the concentration of stock of 100. Say samples. Volume stock. Concentration. Analyte response. Internal standard. Response. So let's start putting in numbers. So this would be sample 1, 2, 3, 4, and 5. Let's say that we have analyte responses of 0.224, 0.498, 0.721, 0.986, 0.1247. Internal standard response 1.456, 1.356, 0.563, 1.445, 1.478. What else do I need? All I want. Oh. Unknown response. Internal standard response. Concentration of analyte. So here we go. Our setup is all ready. So what we are going to do, we need to enter our stack volumes. What is our stack volumes? Let's use 20, 40. Let's use 26. And let's say that our concentration is something that we are going to calculate. So what are we going to do? This is going to set equal. So we're going to use the same exact formula that we did before. Our initial concentration multiplied by the volume we're going to carry over. So initial multiplied by the volume we're going to carry over, and then we're going to divide it by the volume of the samples. I want to note that we should use dollar signs there and dollar signs here. Enter. Good. Yank this all the way down. Here we have our concentration values now. Now we want to get our analyte over IS. So again, in equals. We're going to set analyte response. We're going to hit divides. Internal standard response equals. So now we're going to pull this down and we have all of our values. Excel is so lovely, isn't it? So now let's go to insert, go to scatter plot. Drop that scatter plot in. We're going to have, we're going to right click it and we are going to hit select data, hit add. We're going to select our X values. Our X values are our concentration. So our concentration is, or not our concentration, our analyte divided by our IS. So here is going to be our X values. Enter. Our Y values are going to be our analyte response. Not our analyte. Whoops, I am making a mistake here. I apologize. So our X values will be our concentrations. And our Y values will be our analyte over IS. Go. Okay, hit OK again. Clear this. Let's add some tables here for tiles. Let's call this analyte over IS. And let's call this concentration. Call this analyte concentration. So now we could right click here. We could click add trend line. Going to display, and we're going to show an R-squared. Here we have all of our information, and we're pretty much at this point, we would be done. We just need a back substitute to find our unknown. So let's say our unknown has a response of 0.559, and we have an internal standard response of 1.448. What will we do? Well, let's rate this equation out. This is going to equal, so we need to, I go back to this, actually, let's name this sheet. Standard. We go back to this previous page. Remember, we have b, or y minus b divided by slope. Just verify. So this is going to equal, well, our y value is not directly given anymore since we essentially need to do a little bit of math, but this is totally doable. Let's open a parentheses. Let's say, oh, and just a note, Excel doesn't like it when you use the arrow keys when you're typing inside of here, and it's something that I do a lot, and I need to make myself memorize not to do it. So just know Excel doesn't like using the arrow keys when you're in the individual box. When you're typing your formula up here in the formula bar, you could use the arrow keys, but in the box, when you use the arrow keys, Excel thinks you want to jump to another cell. So just to note, no arrow keys inside the box if you don't want it to yell at you. So what we want to do is we are going to set this equals to our analyte response divided by our internal standard. So now we get our analyte divided by our IS, which is our Y value. So we're almost there. We have our Y. We need to subtract it from our, let's actually add a whole other parentheses around here because we're going to do that anyway. So this is going to be equal to b, which is the y-intercept. So y or intercept. So we have intercept right here. And it wants to know our y values. This is our y values. And then it wants to know our x values. So our x values are the concentration. I hit the arrow key again. Doesn't like it when I do that. All right, I'm going to use this formula bar up top. Let's see, maybe. So now I have the y-intercept, or the y minus b. Now I got to do divided by a slope. So this equals to slope. We want our known y's, comma, our known x's, close parentheses, and hit enter. And it wants to fix something. I don't know what it's fixing because this looks exactly the same to me. Oh, it doesn't need me to type the equal sign. Value that it can't solve. Solvable. Divided by slope. Slope is known x's. Comma. There we go. I must have not included something. There we go. We use these formulas, and as a result, we have the concentration of our analyte. So this uses the internal standard method. Finally, let us look at the last method, which is the method of standard addition. Let's standard addition. So let's start out in the way we've been starting out. So concentration of stack. Sample volume. And we are going to need here is volume of unknown added. So let's say the concentration of our stock this time is going to be 20. Concentration of our calibration, our sample volume, be 100. Let's say we have our sample. Say we have our spike. Let's say we have our spike volume. Spike. Sample 1, 2, 3, 4, 5. And remember the initial spike is going to be 0. Let's do 2, 4, 6, 8, and 10. Your response is 3, 6, 8, nine, 4, 2, 2.59. Saying, what am I missing? We're going to calculate the concentration now. And the concentration is going to be equal to this multiplied by this divided by same exact logic we've been doing so far. Let's put some dollar signs on this. Okay. Dollar signs. Equals this multiplied by this divided by this. Just oh. So at this point, we have the concentration of the spike that we added. So we know the concentration of the spike. We also know the volume of the spike, and we know the constant or the response that the instrument gave us. We know the concentration of the stock solution that we used to make the spike, and we know the total volume of each of these samples. So each of these samples are 100 milliliters. We also know the volume of unknown added. So to each of these samples, we have 10 milliliters of unknown added for each of them. So pretty much this unknown has actually better to write it like this. So at this point, we can set up our calibration curve. Actually, add one more thing. Concentration of analytes. Say this is awesome. Let's create our scatter plot. So insert chart scatter plot. Right click, select data, add our x-axis. So our x-axis is going to be the concentration of the spike. Our y-axis is going to be the response. So we've generated the following graph. Okay. We could right click, select data, right click, add trend line. Going to display equation and display R squared value. this point we have our line and we are nearly done with our problem. We just need to calculate the concentration of our unknown. Remember, what we are trying to do is calculate when this graph equals 0. So when this line intersects with the x-axis. So what then that happens is y is equal to 0. So when y equals 0, in order to solve for x, we get negative b divided by the, divided by x. Not divided by x, divided by m, which is the slope. Just does not want me to use the word slope for some reason. There we go. So what we're going to do is we are going to go into this box and we're going to hit equals. We need to find negative b. What is negative b? Well, we are going to hit negative. And what is b? B is essentially the intercept. So we see intercept. Known y's. The y values are going to be our responses. The x value is going to be our spike concentration. Close parentheses. And now we need to divide this by the slope. So SLP. Select it. Known y values, response, comma, known x values, close parentheses, hit enter. So this is the value that I am getting. So there is one more thing that we need to do to this before we complete this. And this comes down to the volume of the sample and the volume of the unknown added. We added essentially 10 milliliters of unknown, so we're going to need to how much the actual amount is at 10 milliliters. So, one more thing we need to fix up. This equation right here, we actually need this to be the absolute value. I was wondering why my value was negative. There we go. So this would be the concentration of this solution right here with no that's been diluted. What we want is the concentration of this unknown. So what we're going to do is tag one thing onto this entire equation. That is, we are going to multiply it by, open parentheses, we are going to multiply it by the ratio of the calibration sample volume divided by the volume that we added. What this is going to do is going to account for the dilution that we perform. And we will get our new concentration of 25.278. So what we did is we pretty much used this formula right here, absolute value of it. And then we took essentially the volume of the entire sample and divided it by the amount of unknown that we put into it, and then multiply that by our value from the equation, which gives us the original sample's concentration. So this is the method that we would employ if we did a standard addition type of problem. So here are the three methods, and I will give you guys this Excel spreadsheet that I did, so you can all play with it however you desire. So this will pretty much conclude things for today, and I will see you next time.